you know, I'm good at chemistry. I like chemistry, and when your first thought when you're good at something and you like doing something is how you can exploit it for money, right? So my first thought is to make drugs, but you can't do that anymore because they made a TV show about it and it became really good, and now everybody and their grandmama wants to make meth in their RV, so you can't do it anymore. The next course of action is to exploit pre-existing infrastructure, So, chemical engineering degree it is then, go to Fallujah, go to, Iran, Bahrain, you know, put a like a oil power plant, oil refinery, and start cashing in the dough. So in preparation for my chemical engineering degree, I looked across a couple of like fundamental concepts, and one of these is fugacity. In thermodynamics, fugacity is said to be one of the more like difficult concepts to understand. It's all across like unfunny memes on like chemical engineering Reddit. Where it's just like that one thing that they keep dragging it on. It's like Pokemon memes. It's like they don't come up with anything new. So this fugacity, I was like intrigued by it. It's like, all right, well, like what's all the hullabaloo about? So I went to go research it, and I understood it. So now that I understand it, I want to teach you guys about it. Hopefully that you may become successful chemical engineers and become rich. So that's what this video is about, how what fugacity actually is, and then eventually how I understood the concepts like that. So you guys can understand concepts like that, so you can the whole world can be just a little bit smarter. Now, fugacity, the Wikipedia definition is in thermodynamics, fugacity of a real gas is an effective partial pressure that replaces the ideal partial pressure in accurate calculations of chemical equilibrium. Oh, what I eat. Oh, fuck me. Now, what does that mean? It means essentially, I'm going to break down the whole definition. The effective partial pressure means the pressure-like value that actually represents how the gas behaves in a system rather than like the predicted pressure by like the ideal gas model. So what this means is that uh, when we use different models to calculate how gases, like interact with each other, usually we use the ideal gas model, which is not the best one to use because it has a bunch of assumptions. The main five are like the particles have negligible volume, the particles have no intermolecular forces, collisions are perfectly elastic, particles move randomly, and average kinetic energy is proportional to temperature. Now, in real life calculations, it's not always the case. So, like when we calculate the pressure, it's not the same as what the actual pressure is. For an ideal gas, the pressure can be directly used in calculations because gas is assumed to follow like these assumptions. But in real gases don't follow these assumptions. Real gases have like they have other things like affecting them. So like something is, let's say, um like oxygen, for example. Oxygen has intermolecular forces because the dipole on it causes it to attract, instantaneous dipole causes it to attract other oxygen atoms, and we don't take into that consideration when we calculate the pressure of oxygen in room temperature. And so that's essentially what it is. It's the realistic pressure rather than the idealistic pressure that we calculate. The second part of that definition is accurate computation for chemical equilibrium. In higher level chemical applications in engineering and chemical engineering, the ideal gas law, it can't always be used to predict, because the assumptions that we mentioned before, because it's a theoretical model, it's an ideal. Nothing in reality is ever ideal. God doesn't never wants you to be happy. God wants you to suffer. That's why the ideal gas law isn't real. Nothing in life is ever easy. So if the ideal pressure is used for real gases under non-ideal conditions, then like when that pressure is too high or the temperature is too low, like the calculation can be inaccurate, and that's how something very expensive blows up. It's like it's like that one thing with the what's the one that Big Bird was supposed to go on, the rocket, the Challenger 2. Is it the Challenger 2? Big Bird explosion. Big Bird explosion. Yeah, the Challenger. Big Bird was supposed to be on the Challenger. Yeah. So like that's another reason why the Challenger, like if like I'm assuming like the Challenger could have exploded because the calculations were wrong. I mean, it's probably not that. Like, let's be honest, it's NASA. But then, if it could have been, it could have been. I don't know anything about the Challenger explosion. But then, This is if like the Challenger blew up, or like like recently Elon Musk. No, what's the other one? Forgot what it's called. The Elon Musk rocket is the one that blew up, the SpaceX, right? It's the one that blew up. That could be due to this. There's a lot of stuff that goes wrong when you use ideal calculations for real world applications. There you go. And chemical equilibrium in a thermodynamic reaction in a system depends on the escaping tendency of the substance. For an ideal gas, the pressure replaces the escaping tendency because like it's the same. But for a real gas, pressure isn't enough. So that's why fugacity is used, to like make up for all those like assumptions that we used before. Different gases have different fugacities, which is what the escaping tendency is. And these values can be determined by two ways. It's either experimental or they can be estimated, you know and they can be estimated using things that are the ideal gas law. So kind of something like, the Van der Waals gas law, which takes into consideration like the volume that the actual particles have. So here's the ideal gas law here that I use normally, and here is the ideal gas law, but using the Van der Waals model. So you've taken more things into consideration for it to be more accurate. You know, and so these real gas models account for the deviations that the ideal gas law doesn't follow. These include like what I said, the van der Waals forces that the oxygens have. That would be taken into consideration for the van der Waals model. The actual measured pressure of the gas and the fugacity are related by a equation, which is fugacity is equal to the fugacity coefficient and the pressure that you measure. And I'm gonna put over here. It's F is equal to phi. It's this one and pressure. So in an ideal gas, fugacity and pressure are equal because it's an ideal gas. You don't have to assume anything, so everything's the same. But um in one where the fugacity coefficient is less than one, that means that attractive forces dominate. So if you have a pressure of 1 atm and the fugacity is like 0.9, I'm sorry, the fugacity coefficient is 0.9. That means that the fugacity would be 0.9 atm. So the actual pressure that we have is 1 atm, but it behaves like a 0.9 atm gas, due to other things. This gas has a lower escaping tendency than is measured physically, you know, and so the fugacity is less than the pressure. But on the other end, if the fugacity coefficient is larger than one, that means that repulsive forces dominate in the gas. So the gas, you know, acts like it has less pressure. Wait, yeah, it acts like it has less pressure than it actually does. So, you know, if your gas has, no, sorry, I'm dumb. Why do I even talk sometimes? I'm getting ahead of it. I should slow down before I say these things, because I'm like, I don't know if it's the ADHD. It's probably not the ADHD. I think I'm just like blaming mental illness, because I don't want to do that. I don't want to be like a bitch. What was I saying? Oh yeah. Essentially, if the fugacity coefficient is bigger than one, repulsive forces dominate, and the gas has a higher escaping tendency than the measured pressure suggests. So it acts like it has more pressure than it really does. So that's why the fugacity coefficient is more than one. There's a good one. I'll put like a standard, like I'll put a drawing, a cool drawing this side, like a cool drawing this side here should be fine. But the thing is, the fugacity is that as kids, like especially since you came straight out of, I came straight out of high school, you're taught like ideal gas is like that's what it is. That's the first thing. It's like it's very intuitive. You get what it's talking about, but this isn't intuitive. It's like it's basically telling you like, oh, everything you learned is wrong, you know? Because it's not just a difficult thing to comprehend because it's not physical. It's a it's a mathematical concept. It's like it's a ratio. It's what you're taking away. You're adding on to the actual value to be more realistic, you know? So you gotta like do a little like aphantasia, you gotta memorize, you gotta think about the apple. You got to think about the apple and like turn it in your hand, and you got to be like, okay, so the measured pressure is this much, but it acts like it has that much pressure. And the difference between the two is what the actual fugacity is. Each gas differs from the ideal gas in its own way. The fugacity coefficient accounts for this difference in how they behave and how they actually behave. The difference between calculation and reality. Since the fugacity coefficient is the only multiplier, it doesn't really have a value. So you're basically thinking about something. The value, not having a unit doesn't help. They're just telling you like, okay, boom, this is what it is. And usually people, when they go to like college and they're just studying, they're just like, mugging it up. They're just like, okay, words, brain, just memorize it. They don't really understand it. So like, you got to think about it in more simpler terms. And what that is that fugacity tells us the effective pressure of a real gas seems to have when calculating an equilibrium, phase changes, and chemical behavior is different than the calculated gas because of things that we don't take into account when you're calculating the real gas pressure. So that's about it. And the thing is that we don't understand these abstract concepts because we as humans we evolved to understand stereomotor concepts. Like at the end of the day, we're still monkeys. We're just monkeys that like figured out how to like make rocks think. You know, so we still have that like biological thinking in us to like understand real concepts. Like this is a rock, that is a tree, that is a person. It is hot. It is cold. The wind pressure is too high. I'm getting crushed by a rock. She doesn't love me. Things like that, like real things. But then when they tell you to think about more abstract concepts, your brain like draws a blank. You're like, what the fuck are you talking about? You don't get it. That's why it's always great to use metaphors. I have loved metaphors. Metaphors are the only thing that have helped me understand chemistry. When I was learning orbitals, I always used to think about it like it's like a bees around a flower. The more energy the more energy the nucleus has, or the more neutrons the nucleus has, the better the flower smells. So more electrons buzz around it. It's like it's like bees. Bees around a flower is essentially what electrons are. So you gotta equate things that like don't really make sense to something that you can understand. Like orbitals and things like that. So the more you equate, like let's take fugacity for example. What fugacity is a correction factor, and so what is something you could take like a correction factor? Let's see. Okay, let's take like a white girl, like a really rich, like a Hamptons white girl. She wears like a hot pink, daddy's Range Rover, four-wheel drive, nothing but Louboutins, like a bimbo, like the girl from Mean Girls, not the main one, not the brunette one, the other one, the one with like the big old bug eyes. I forgot, what's her name? Mean Girls Bimbo. Mean Girls Bimbo. Karen Smith, is that her name? Hold up. Yeah, that's the one. That's the one. The one that's mom is like Parks and Rec. Yeah, this is the one. The one from the girl from Ted 2, the lawyer. Right. Imagine her, right? She is an idealized version of the character. But then something you got to realize, if you meet that someone like that in real life, they're not gonna act entirely like her. They're based on that, but then like there's a lot more realistic that you gotta add to it. She might be going through like a breakup, or like her dad doesn't love her, or like she's multifaceted. Maybe she's really into baking. Like she's a bimbo, but she's like I feel like baking's too like it's too like misogynistic. What's something that she could be good at? I have emotion. I am feeling bad for a made up character that doesn't exist in my head. Empath, ladies who want me. But it's like it's just like you're taking an idealized model and you're making it real. So when you put that into something that you can actually like understand it, like imagine in your head, you become better at it. You can like you can get through it. So when you think, you use like you use metaphors as a bridge from something that you understand to something you don't understand. And it's like you're layering it on top of each other. It's like, oh, okay, so this is how it works. And that's basically how you gotta understand these like abstract concepts. It's like what David Lynch does when he's with. I love David Lynch. Go watch Twin Peaks. Go watch Eraserhead. Not on any drugs. So do not watch Eraserhead on drugs. It is going to be a bad time. But the thing is that when you understand abstract concepts like life, death, like pressure, mathematics, anything like that, you gotta feel you gotta feel for it more than like what just you see or just your imagination. You gotta use your emotions. You gotta get really into it. The best scientists, you know, they don't really see math as a science. They see it as music. They see it as art. Because high level math and art are they're indistinguishable. They're around, they're the same thing, and it's something beautiful. And you got to really have heart to understand that. When something is, it's a very human part of us to make an emotional connection with something to help us understand it better. That it's what we do with people. So why can't we do it with abstract concepts? It's something to make us understand it better. Because all concepts are they're just really like focused people. There's no people. The concepts are just people that are like really into one thing. A really really autistic guy is just a concept. You know, like he could be like really into one thing and he's just that concept, and you just got to get to know the guy. You got to bring him over to your house. Like milk and cookies, whatever autistic people do. Autistic people, Santa is Santa autistic? Anyway, that's what I'm saying. So at the end of the day, when you're understanding abstract concepts like fugacity, you got to put emotion into it. You got to feel it. So that's how you get around to understanding what they actually are.